Okay, perfect. You see my screen?
Yes.
Yes, but it's not in presentation mode.
Oh, just a second. Is it the notes or
It's the original one.
okay?
Now you have to switch it. You have to swap the display.
It's the notes, right? Okay.
Yeah, this is with the notes.
Perfect.
Yeah.
Yes. Thank you, Mira. So, hi everyone again. Now we have we can have it like as a discussion or um, like as an exercise about the information creation and tools and data that we use in water resources management. So, just a recap for what we said before, maybe 2 days. The baseline water resources inventory, so which is like documentation of the current water uses and water supplies available for meeting the current and future water demand. So, and also after defining the boundary of our study area. So here we will go to information creation. So in order to do this baseline assessment. So we would focus on type of data and information that are commonly monitored in water resource management. And this could include rainfall, stream flow, water quality, water quantity, and so on. So information creation involves collection of and a generation of data and information on water resources, as I mentioned, and this information then monitored to identify the changes in water availability and quality over time. Also to detect the emerging issues or risk that may require actions. So how data and tools help conducting baseline water resources inventory. So like regarding the data, as you see here, like there is a global data and hydrological cycle components. The hydrological cycle components like precipitation, evapotranspiration, and so on. And also the global data on the status of the water resources management and other related domain, like land use, land cover. So data and tools, and as you said, as you see also here, the tools, also there is tools for data analysis and tools for data processing. And of course, we will need the open source tools. So data and tools can greatly assist in conducting the baseline of water resources inventory by providing a comprehensive understanding of the quantity and the quality of the water resources in a given area. So these tools can be like mapping, spatial analysis, like using the geographic information system, GIS software, for example, on a runoff or on water quality. And these can be mapped and analyzed to understand the spatial distribution of water resources in a given area. Also, there is the remote sensing that we always mention. The remote sensing techniques, such as the satellite imagery, can be used to monitor also water resources, such as the changes in water level and water quality and land use. And this also helps to identify trends in water availability and usage over time. Also, there is, as Lars was mentioning at the end, which is the hydrological modeling. So these models can be used to simulate the movement of water through watershed, or for example, groundwater system. So this can help to estimate water availability, surface water, and groundwater interactions, and the impact of climate change, of course, in water resources. So data collection and monitoring, like like water resources data can be collected through monitoring programs that measures this component. So in order to use it for further assessment. So let's go a bit on some global data on hydroclimatic conditions like precipitation, temperature, soil moisture, evapotranspiration, runoff, relative humidity, and so on. So these are like some platforms, open source data that you can use to obtain this component. Like we have this hydrometeorological data. We have this, for example, this website, the two Timebo, and you can obtain from the air precipitation, temperature, relative humidity, and it's globally also wind speed. But before I start with these platforms, I just want to mention that these platforms is a collection from our colleagues here in the university, and like we're not like aware of every website, but like we combined all of them. It was like an effort combined, like from everyone. So I was checking this website, but now I think you have to pay for it. But I think it's not a lot. But in the data is really reliable there, and I just put it here. And also we have like another website, for example, like this one, the CGR. There is like global high resolution soil water balance, and also potential evapotranspiration, global aridity index. Also, one of the main components in hydrological cycle, which is the precipitation and evapotranspiration. So there is many products, as we said, like for remote sensing. For the first product is, I mean, I just put some products here. I mean, there is many products. So there is this one, Emerge. It covers like the whole globe, and it will be, I mean, it covers from this like coordinates, and the time scale, it starts in mid of 2000s until now. So it's really, really good platform for precipitation. And the format is TIFF. The TIFF, it means the raster, as I mentioned like yesterday also. The raster is like an image with pixels, and each pixel has value for this precipitation. And this one, you can just put it in GIS or in any programming language and manipulate it easily. And also there is another formatting. They have also NetCDF that I also mentioned yesterday. The NetCDF format is like another type of data, but it's better to have less storage, but also if you want to manipulate it and everything, I think sometimes it's better to convert it to a TIFF or to a raster. So with the temporal resolution of 30 minutes, so this product can measure the precipitation each 30 minutes, which is really high temporal resolution. Also, spatial resolution is 0.1 degree, which means 1 kilometer. So the author is NASA. Another platform, which is ERAPI, and also ERAPI Plant. There are also the analysis data coverage, the global time scale is from 1959 till now. The format mostly is the NetCDF, and here you need to convert it, as we said, but it's really, really good platform. They have like, this is the temporal resolution, the spatial resolution. They have like hourly temporal resolution and so on. So I will not go through these details, but just to mention what are they. As we mentioned yesterday, the temporal resolution is the time that they capture this image, and the spatial resolution is the size of the pixel. So you have also this SHERPS, which is really widely used, and it's a raster directly, but the resolution here is 5 kilometers. So sorry, here 0.1, it means 10 kilometers. So we have also the evapotranspiration. We have this vapor. Vapor, actually, we can go through it after I finish the presentation. Actually, it covers Africa mainly, and they have like many products, not just evapotranspiration. They have also land use classification. They have precipitation as well. They have water, crop water productivity, and many other components. And also Era 5 and Era 5 land, also they have the evapotranspiration. They have also, like, if you are interested, like a snow, the snow or the temperature or many other components. And there's also the gleam, which is the actual evapotranspiration data. It covers also the globe. It's also daily. Let's see, the resolution is 0.25. Not the high resolution, but I mean, you can do it in some study areas, like with some, like, for example, the Blue Nile. It's very big catchment. You can use it there. Here's some data regarding the land use and land cover, if someone is interested, because sometimes we need to assess that as well when we do the inventory for our catchment. So I just put some products here, which is like the first one is the Modest. I don't know if you're familiar with that. So Modest is a really powerful tool, and they have a special resolution, 500 meter, temporal resolution annual. But for a land cover, it's fine to have it as annual, like not as a precipitation, because land cover is not changing every day that fast or something. And the special coverage is the globe temporal coverage from 2001 till present. There is another also, as we mentioned already, the vapor from FAO. So also it's like spatial resolution, 250 meter, 100 meter for some countries. It's annually also. And the special coverage is Africa and Near East, mainly Africa. So it's from 2009 till present. Also, it's really good information to obtain and to analyze the land use and land cover. There is other websites, like we will share this presentation with you later on, and you can like have this collection of websites. Like for the geology and soil, like the USGS and the network for soil map from FAO. There is also other related domains like climate data. We have this World CLIM, so it's really website. The coverage is the global time scale since 1950. The format is GTEF. GTEF is the raster, as we mentioned. Resolution, current, past, and future also. So this website is really good one for climate data. And also, like I put here, one of the tools, other climatic parameter multi-hazard dataset. So we have, like, there is a tool here, drought risk assessment tool. So this toolbox has been completed by the Joint Research Center of the EU Commission, and it's from 2000 until 2018. So like for different geographic scale. So it's composed, as if some of you have experience with drought assessment, it's composed of three main approaches, which is the exposure, how this area is exposed to drought, and the vulnerability, how it's vulnerable to drought. And vulnerability, you can measure it in many aspects, like it can be also from the government, like the government, they don't have the adaptation strategies to adapt with drought. That means they're vulnerable to drought. And the hazard, like, which is the risk itself of the drought, or the scale of the risk. So, I mean, all of these are the open source data, and I think it's pretty useful to do them. Even if you're approaching another way, sometimes it's good to include some other component to analyze. There is also other related domain. These data, like related to human environment, like the development status, like the GDP, development indicators, education statistics, gender statistics, health statistics. Sometimes I'm doing like water resources assessment for the basin, but it's good also to mention this information. For example, if I mention the gender statistics, or like the GDP, how is the GDP in this area? So it will give me an indication how they can adapt to some crisis in waters or natural hazard or so on. Also the population, the poverty. This is from the World Bank, and this is another website from Sustainable Development Goals and the Socioeconomic Data and Application Center. So also, like other useful data engines, sometimes more, not sometimes, I think it's most of the time that before starting with the assessment, they need to to know the topography in this catchment and to know the elevation in this catchment, because the elevation, it plays an important role with everything in the catchment, also in precipitation. Sometimes in high levels, like the precipitation is different than low levels. So there is also like this website, Earth Explorer. We also can go through it like after I finish. How to download the data of the elevation. I think the DIM is really important then to have. So now you go to tools, using tools in the baseline assessment. So there is many tools that we can use. How to use the tools to represent the data that we have. For example, we have the Excel sheet, the Excel application, which is like we can use it for time series analysis to have trend detection, homogeneity, and descriptive statistics that we can read and understand. And also we have these programming languages, which is R and Python also. This is a really powerful tool to represent the data and also to manipulate the data. Some type of data that you can just use these programs to manipulate it or to use it for your purpose. So example of some tools that it's always needed in water, like I will just go through QGIS. For me, I mean, this is one of the basic things that you like anyone is doing the assessment you should know some basics about it. And the R programming language, which is like much, I mean, for me, I would say like it's much better and much faster than QGIS. You can do many things with this programming language, and it's open source as well. Google Earth Engine and others. Like here, you can just go through them. So here, as Lars was mentioning about modeling, I don't know if he put this slide or not, but I mean, these like are different models that we are using in water resources assessment. So it helps in hydrological, it helps in environmental assessment, water allocation models, accounting, stakeholder mapping, etc. So here, as we see, like there is hydrological modeling, like there is the mod flow. I mean, yeah, I mean, I think some of you are familiar with it. We're not, for me, like personally, this is, as I said, like it's a collection from colleagues. I'm not like know like how to function with everything, but this is like a collection of models that you can also relate if you want to do like water allocation. There is like a list of models that you can read and understand more about. So, and there's also SWOT, HPV, and for water allocation modeling, there's the WIP and river wear and HIC RSM and Mike Basin. There is also the geoprocessing, which is remote sensing based prop yield. Here we can use ArcGIS or QGIS, watershed delineation. So here, the delineation is very important. Sometimes you don't have the borders of your catchment that you want to assess using QGIS. So delineation, this is another process that you have to have the digital elevation model, as I mentioned before. And from the digital elevation model, you can have the stream flow, you can have the flow accumulation, you can have like some step at the end, you will reach to, you will do the last thing, you will do one function to give you the border of your catchment, which is the natural boundaries, as we mentioned before. And these natural boundaries, it came from the elevation, and elevation, it will show us the stream flow and how it, I mean, at the end, the catchment is surrounded by mountains or anything that any drop enter this catchment, it will go to the middle. So if it goes beyond this point, it will not go to this catchment. So this is not our borders, inside our borders. So delineation is also really important skill, I would say, that you need to learn to have your catchment, because in many areas, the government, they don't have the borders of the catchments. You have to delineate it yourself. And also there is land cover classification, also using ArcGIS, QGIS, R, interpolation, time series analysis. Also there is stakeholder mapping, crop water requirement. There is also a model called CropWatt, give you the crop water requirements and how much do you want to irrigate. So if some of you are interested in agriculture, for example, instead of just irrigate without measuring that, sometimes it affects also the plant, and also it's like consuming the water. So tools like information creation, as we said at the beginning. So what's the goal of this and how it starts? So it starts from the demand. There's demand in this area, and then we have a demand models. Then after the demand, we want to allocate the water, so we go to allocation model. And from here also there is land use and soil, and from that we need also we have also the climate data, and from that we have the rainfall model, the runoff model, runoff from land use and soil as well, because soil is playing an important role in runoff, like infiltration, or is it fertilizer? I mean, the water can infiltrate or not, or the land use, if it's like urban, not urban. And then we go from the demand and these input models to allocation models, and then we have the output, and then we have the result interpretation, which can be done in scenario analysis, water security per sector, water allocation. Maybe there is a potential for rainwater harvesting here. Also, we can assess drought and so on. So information creation and tools it's very important to understand what's happening there. And it's also very important to know which tool and which model and which data that we need to in order to achieve our goal at the end. So here, maybe I will not explain here in very details, but it's a ready tutorial just for basic functions in JS. I'm emphasizing in JS or QGIS, so you can start with that because you need data to manipulate, and the best way to start is in QGIS. So as you know, like this is this website, this application is or software is used to create spatial data and to investigate spatial relationship between the data. So it's very useful tool when it comes to water resource assessment. You can create maps, and this map represents the result that you want to achieve, and anyone can read this map, can know what's happening with just one map. So as I mentioned yesterday, someone asked me, how can I have the data inside my catchment? So for example, you have the digital elevation model. This is your catchment, and then in the red lines, and you have this digital elevation model as a raster. And this borders not raster, it's like, as we also said, it's a vector, which is like just represent the boundaries of the basin. So you have all of this. I just want the data inside my basin because I have a legend here and I will be confused to know where is it like. So first we need to clip the raster, and this is a tutorial how to do it in QGIS. I mean, you just need to install the QGIS, nothing else, and then you follow these steps. There is like a function here, clip raster by mask, and then you will this window will open, and you just put here the raster and here the watershed, which is the boundaries, and nothing. You can just save it and run. And at the end, we will have this just clip to our area, and we will have the legends, as we see here, the legends according to the data inside our study area. So this is for the earth catchment. You saw it before in the first exercise. So at the end, we have like some maps, and these maps, as I told you, like it represent the result, and we can read it. And these maps were done by using QGIS or ArcGIS. I mean, rather than they have the same output. So here we have this basin, which is, I think, the Blue Nile. It's between Ethiopia and Sudan, and as you see here, we have the elevation, and then from this elevation we can read the map, and we can see like here there's a high elevation, here there is low elevation. Also here there is the infrastructures, like the dams, where are the dams in the basin, and from this I can understand how many dams in the basin, how they are distributed. Also with these river networks, I can know if these dams are located in a good places or not. So I mean, also there is rainfall stations that I can know where are the rainfall stations and if they are like sparely distributed or they are well distributed. So also here we have the precipitation as we mentioned. So how can we read the precipitation if they are distributed spatially? So here are the legends, and this is in millimeter. And I can know, like in this area in Sudan, the precipitation is from 300 to 600. Actually, this basin is relatively big basin and huge because it covers Ethiopia and Sudan. But if you have also small catchment, it will be more representative, like with the small pixels. And they can know like the precipitation here, and here, like there is the highest precipitation. And this can be to too many reasons. Like I can also analyze this map at the end, especially from the topography and so on in the climate. So also there is another examples for the temperature as well. Same thing here. You can just put the raster, manipulate it. And if you see this map under this one, which is the base map, and this map is already exists in QGIS or ArcGIS. So you just add the base map and you manipulate your data so we know what is the space and at the end. So also there is another example, which is here, for example, the population density. So I can understand, like if I have the water infrastructure and I have the population density, and I can know if this is like the infrastructure is located in a good place or not, or if this place like it's highly populated and I need more infrastructures here or something. Also there is a map here for groundwater potential. So this is a really powerful tool, the QGIS. And also I will share with you one link some of you already sent me, and I shared with them a YouTube channel, like as knowledge transfer, I would say, to share this, because sometimes I just go to YouTube and I want a good channel, and sometimes I'm confused. But this one, it's really good channel, and it almost covers everything in QGIS if you want to learn. So also, what can I get, or what can you get from other data? This data, you can get it from the FAO and like the water resources per capita from FAO, and also the population estimation from the World Bank. And then you can know the water security and water availability per capita in each country. For example, this was an assessment for Ethiopia, Sudan, and Egypt. And if you can see, they are all here, which is water stress level. But before it was like they were good, and now they're going. I mean, almost here, and in 2050, it's projected to be like worse and worse. So just I represent the data in a graph, and I know what's happening there. Also, if I have like some graphs like this, the total abstractions in Sudan, as we see here, like agriculture is dominant and it's taking like 96% of the water resources there. And here we need some solutions, like because it's consuming a lot, the agriculture. And is it like beneficial at the end to consume all of this water in agriculture or not, or it's like over consumed or over abstracted? So I think this is the water from groundwater only. So the groundwater, maybe it will be threatened to be depleted or something. So need here in this data or statistics, we need to find some solutions. So I would say that was it. Thank you for listening, and we would be happy to for some questions. Is there any question, or we can go? Oh. Yes, Hila. Hila, you raised your hand.
Hello.
Yes.
Morning, Mr. Bilal. Just to take you back at the beginning of your presentation where you talked about available data sets, those that are there online. There's where there's actual evapotranspiration and evapotranspiration. Just highlight the difference between the two, or whether one needs to apply a factor to those data sets before using them, because I see some you mentioned actual evapotranspiration, then others is actually just evapotranspiration.
Yeah, of course. So
that's my question.
yes, thank you. That's a good question. And also, I mean, here for the evapotranspiration, we have two types. The first one is potential evapotranspiration, when there is no word besides the potential evapotranspiration, which is the potential, they measure like according to the temperature and these other parameters, how potential this water to evaporate. And the actual evapotranspiration is the actual water that evaporate from that area. So sometimes it's good to use the actual evapotranspiration, but sometimes it's like it's evaporating from different sources. Like the potential evapotranspiration, I can estimate it from precipitation or from other sources, but actual it can evaporate from rivers. It's not from the precipitation that were like as an input for this catchment. So depending to your goal, you can decide which evapotranspiration type you can use, I would say.
Okay, yeah, thanks. Because I felt like that word potential evapotranspiration was missing. But from here, I don't know if you can just go back to the slides where you were sharing those data sets. There was only way you could mention like evapotranspiration. So I was just wondering whether it's actual or is it potential, and also
Yes,
whether you need to apply a certain factor to it before you bring it. Yeah, all right,
yeah,
thank you.
you're welcome. Yeah, James.
Yeah, morning.
Good morning.
I would like to take you back to what I asked yesterday.
Mm-hmm.
Then you gave me a particular answer, or you suggested. Okay, I would like to take you to the question which I had when I said, when there are missing values for the data that you are looking for, what do you do then? You suggested that we can use products that are complete, meaning you not have to enter the values manually.
Yes.
You just get to specific products. Yeah,
Yes.
so I've seen from the products that you are given, the same question again has come back. Some of them, they range from 2009 to present, and then some of them may not have the entire set of variables I'm looking for. So for example, my variables are 8. There is precipitation, minimum temperature, maximum temperature, average temperature, wind, relative humidity, and sunshine. So there is still that missing element of 1, the years for certain products, then 2, for certain products, they do not have the whole range of variables that someone may be looking for. So how do you deal with that?
Actually, this is a bit tricky and critical, I would say, but maybe, I mean, I should seek the data. I mean, at the end, if I have like the project, I should seek the data from other sources, like with a long time series. If I don't have like some of the variables in the same time range, I don't know how is it like in your catchment. How is it with the, for example, the local like governmental institutions, if it's available or it's not available. But for me personally, I would try to seek for that. Otherwise, I will change my time range or something, because it cannot be I mean, also depending on the purpose of your study, like if you can have some variables with short, as I mentioned before, like we're doing like this merging strategy with remote sensing and ground data for precipitation, but we have some products are not in the same time frame, and in this purpose, it was fine to do it because I'm improving the ground stations, and some products will not cover this time range, and some product will cover. But other analysis, maybe you need the whole variables in the same time series, and in this case, you have to seek for the data either from open source or from the governmental institution, or to change your time frame, I would say.
Okay, but then is it allowed to combine, I mean, batches of data? For example, you get from one product 4 variables, and then from another, the other 4 variables, like I have 8. Then you combine the data based on the historical account.
Yeah, I think for this, you can do it. What I was saying yesterday, if it's the same variable, but you're putting like from different sources in the same variable, like humidity, and you put 10 years from this source and 10 years from this source and 10 years from this source, maybe at the end it will work, but it's not that reliable because the data capturing is different.
Okay.
But for different variables, I think it should be fine.
For different variables, meaning you get, for example, for precipitation from one site,
yes,
then maybe temperature another site,
yes,
then you can combine the two.
Yes, because I think it's almost impossible to find all the variables in one website.
Yeah, in one, yeah, that's what I've discovered. So when I went through the sites, I could not find one which has all of them combined to, I mean, in one place.
Yeah. So
okay,
I think it's fine to use. You're welcome.
I would also say that you take into consideration that the graded data you are using have been validated in your area. Like you have a lot of graded data, but it's better to choose one that has been validated to your area of interest. Maybe your country, your basin, the Africa. Some products are working better in Africa than other places, and then other work in vice versa in other areas. So it's better also to look what graded product are using, because you have to choose one that's working well for your basin.
Okay, thank you so much.
Thank you so much.
Just to interrupt and maybe add a little bit of clarity, Mr. Jimmy Katambu, sometimes it's not that the data is missing. I think also when you want to use a particular data set, consider things like when a satellite was launched. These are missions. For example, if you take Sentinel, it was launched 2015 or so. So you might not say maybe data is missing from 2000. And then to overcome such things, you could use maybe a Landsat, which has got, a longer time span. And then if indeed there is actually a missing data set or portions, for example, with Landsat 7, there was a point that a sensor could fail and produce a line. There are techniques that are actually meant to, interpolate in between, and then you have a clean image. So one of the things we have to consider, Mr. Katambo, is when was the that particular mission launched, before maybe you say data is missing. And then if it's actually missing, I'm sure there are solutions in some discussion groups online that, they have, come up with techniques to, fill up the missing gaps. There are techniques like Akima spline that you can really use to interpolate non-linear data, and they're very, very good. So if you really need to use a certain range, or you can't change your date, I would advise maybe you kind of calibrate 2 data sets where they are overlapping before you can just jump and use so before you can just decide you are shortening your time range. If you want maybe say 20 years, where the 2 data sets are overlapping for different missions, if you validate and see the differences, you could actually apply a correction factor to have your 2 separate data sets standardized. from literature that I've seen and read, for example, if you are looking at radar altimetry, it's possible to combine different data sets as long as you can calibrate or validate even better off with in situ data.
Okay, so thank you, Tafila. But then the other part of the question is when there are many variables, like in my case, there are 8 that I'm looking for, and yet those sites are not giving me the 8 at the same time. So that was the other part of my question.
Yeah, so I think you can go ahead with variables that you can get from one particular data set, and then you can get the other from one data set. If I had Bilal and team clearly is that you can take variables from one, but for example, if you are doing precipitation, it won't be ideal to have precipitation from one data set and then you just jump onto the other, like CHEPS and the others, because one, they might have different temporal resolutions, they might have different spatial resolutions. So if you are taking one variable from one data set, then that's fine. For example,
Okay.
potential evapotranspiration, then if you can also take maybe a precipitation on another data set, that's fine. As long as all your variables, you have consistency among them. It would not really be a problem if you are, for example, using a rain gauge station in one particular area, and then on the other area, you also have maybe, say you have 2 rain gauges that are recording that are recording at the same temporal scale, but say maybe within your basin or catchment, you can use those. But the only problem is if you want to use a satellite data halfway, and then maybe you take an in situ data, because definitely one thing I know about remote sensing images that they could either be underestimation or overestimation of a certain parameter. So if you decide to stick to one, just take one from one data set. Other variables, you can also take them from one, but they should be consistent within the time series.
Within the time range. Okay, thank you.
Thank you, Tafila. That's, I think, it's really nice also to have feedback from each other. That was really good input. Thank you.
Thank you.
Okay. So any other questions? I would. Catherine, I think, as you said, like we can go to the section of Lars, but if there is no questions, we can also go there to go through it fast. I can also show you fast the output. I don't know if you're familiar with this platform, but it's really useful. You see my screen, right?
Yes, we can see it.
Okay. So here, as I told you, like it's mainly for Africa and some parts of the Middle East here. If you go to catalog, you'll find here many data sets, which is, for example, water productivity, actually evapotranspiration, like precipitation as well, evaporation, like also sometimes for specific areas or regions inside. So, and this covers like the good time range. So from here, I think this website and also land cover classification here, for example. So yeah, I mean, I would highly advise to use that as your study areas, like in Africa mainly.
I would like to also add, like for vapor, like for the land cover, it also covers like if you have irrigated crops, if you have rain-fed, which like in MODIS you want to be able to find. So it has more classes and it's more detailed, I would say. Like if you don't have real-time data or you can't go to the site to see.
Yes. Do you see my screen?
Yes.
Is it the notes or?
No, without the presentation mode.
Okay. So I would just go through like the last slides of Lars, if like because some people are interested, and I think those are the models that Lars said, like for that we managed to use in our institute, and it's pretty much similar to what I explained in that slide. So there is like some models for flood risk, irrigation, reservoir operation, and so on. So also we have like this hydro statistics. I would say like it's very important to represent the data, which is like, to detect the trend. So in the graph we can have an idea of the changes of the annual precipitation first, as well as the mean annual and cumulative deviation from the mean annual from like 1980 to 2015. So hydrostatistics is used to monitor and predict water levels, identify water-related hazards, and manage water resources. So it can also be used to assess the impact of human activities or on water resources, and to design strategies to protect and manage water resources. So also to inform water policy decisions and to develop strategies to reduce water-related risk. So the long-term average is often used as a baseline. This one as a baseline for a reference point for comparison to current and future values of the variables. So it can help us to understand whether the current values are above or below the average and how much variation there is in this data. So for example, if the current temperature is significantly higher than the long-term average, it may indicate the heat wave or other abnormal weather pattern. Conversely, if the current temperature is lower than the long-term average, it may indicate a cold snap or other unusual weather event. So the uses is to provide quantitative understanding and to monitor the changes and to identify the trends. So also we have the variability, as we see here, like variable refers to degree. Like first, it's important concept because it helps to understand the range of distribution of water-related variables and to identify the pattern and trends in water. So variability is a key component of hydrological system, and understanding it is crucial for like water resources management. It's crucial for water resource management for further goals. So if you see here, like the spatial resolution as like high resolution here, I don't see the pixel, like the pixel size as I see it here. Like you see here 1 pixel with 1 value, 1 pixel with 1 value, and so on. But here the pixels are small, and I have better representation and also better variation of this like rainfall. And here the very low resolution, which is like just 1 pixel covering the whole basin, So this is for the rainfall, this is the groundwater recharge, and this is groundwater storage. So the types, like they are like spatial variability, like difference in water-related variables that occur over different regions or location. Like, and there is like the interannual variability, I would say, like the changes in water-related variables that occur from a year to year. Example, like changes in annual precipitation, river flow, and groundwater levels. So this is regarding the variability. Also, there's some like seasonal variability, as we see here. You can see the season here in this graph. Changes in water-related variables that occur over a course of a year. So changes in a river flow or precipitation or a temperature. So it can be noticed from the graph, like in the upper left, the seasonal variability for the precipitation chirps, evapotranspiration, and the water yield. So you can notice here, this is the legend that you can see, like how is it like the precipitation, for example. I can see like, okay, the rainy season starts in June and ends in September. So this is like for the variability, and also there is like optimization and planning. Just a question, did Lars went through this? I don't think so, right? I think that's a no. So optimization, like when you have like, okay, thank you. So it involves making decisions that taking actions to allocate, use, and manage water resources sustainability. One approach to achieve sustainable water resource management is through optimization technique. So optimization involves like finding the best course of actions among like some alternative based specific criteria or objectives in the context of water resource management. So can be applied to various factors such as water allocation, water quality, water efficiency, and so on. So we have like two types, which is the operational and strategic optimization. Operational level can be used to determine the optimal operation of water supply and distribution system to reduce, for example, the energy consumption or to minimize water losses. And strategic can be used to determine the optimal allocation of water resources among competing demands, like to evaluate the potential impact of climate change on water resources, or to identify the best mix of water management strategies to achieve long-term sustainability, and so on. Like this is just a graph to the as we see like a sustainable optimization approach for essential irrigation. As we see here, like we have the season irrigation planner, and when they change here, everything change after. So at the end we have like different result whenever we change the irrigation planning. So also it's like in recent years, artificial intelligence, like we're like hearing that a lot, that has emerged as a promising technology with the potential and revolutionize various research areas, such as like in many areas, and including also the water management, I would say. So it's like technologies have advantage of being able to handle complex nonlinear relationships and accurately understand the dynamic of water treatment or water resources processes. So this enabled them to monitor and to predict water, for example, quality. And we just talking here about treatment, for example, water quality, detect pollutants, and optimize optimize the use of water. So leading to shift from reactive problem solving to proactive risk management. So it's also real-time monitoring. Water quality and usage can change rapidly, and it's essential to monitor these changes in real time. And artificial intelligence can provide a real-time monitoring. Also, early warning system using artificial intelligence by using this technology algorithm to analyze historical data. Water managers can can identify pattern and detect if there is like threat in the future, and give us like early warning about specific hazard or any problem facing water. So I have like just some applications of artificial intelligence, for example, for the data. There is like the data mining and pattern recognition. Like we put all the sources for some of them if you are interested to read also. Data cleaning and pre-processing, data integration and merging, let's say, as we're working, as I mentioned before, forecasting as well, stream flow forecasting, natural hazard forecasting, water demand forecasting, and also others like water allocation, leakage detection, irrigation management, and so on. And if you want to read more about those applications, you can just go to this link, and it's a really good source to understand more. So here also there is like water monitoring and measurement, as like Lars, I think, mentioned in lecture 3, like the graph, like the essential parameter of our system that requires measurement to manage and quantify the water within a system, precipitation, evaporation, runoff, and soil moisture, and so on. So here, like just a recap for what we said before about the systems. And this is the basin boundary, as we see, like we have here. Let's go like precipitation, evaporation, transpiration, and I need to measure that. So I think also Lars mentioned those. So traditionally, precipitation amount is measured using rain gauge, which is considered the most reliable method to measure precipitation. However, now estimation lacks of spatial component, and their estimations can't be generalized over large areas. So also there is like, for example, there's one of the satellites for remote sensing to detect precipitation, evapotranspiration. There's the evaporation plan, azimuth, and the ED covariance tower. Like this is just some methods that they collect data, I would say. So there is like here for the runoff, the wire measurement, like it's as you say, like as you see here, it's a wire is structure placed across stream or channel that causes the water to flow over, and it controlled in a controlled way. So by measuring the height, of the water flowing over the wire, the flow rate of the water can be calculated. So this is commonly used for smaller stream or channel, and this is also the flow measurement and others. Area velocity method, I think it's also like commonly used. So yeah, and here also some methods for soil moisture. Sorry, and I think that's the rest of the slides of Lars. So, do you see my screen?
We see the presentation, like with the notes. It's not on presentation mode.
Yeah, but I don't know, it disappeared from me, the screen.
Maybe
Can
stop sharing and
I
share
couldn't
it.
find. No, I couldn't find stop sharing. Can you make it? Can you stop me from sharing? Because you're a host.
Let me try.
Yeah, I can stop you from sharing.
Yes, thank you so much.
No, it didn't work, sorry.
Maybe it's on your extended screen.
I will try to.
I will try to do something. Okay.
Yes, now I saw the Zoom again. Okay, now you can. It's okay. Thank you. I think it was the rest of the presentation from Lars. So I hope it was insightful. So there is some questions. So I don't know if there's more questions, but if there's not, I think you can also stop. So at the end, you can just think about these tools and this data, and what type of data that it would be the best for your research and for your study area, and what kind of tools would be the best also for your study area. And we would, it would be good if you can put that in the mail word, so we can know and read and also interact with you. Or if someone wants to say something now, which kind of data or what type of tools that he or she can use, it would be also good. So okay, perfect then. So I think